Second
Okay.
session.
Okay.
Second present.
Second speaker. Okay.
Yes, second speaker. Thank you.
Okay. Okay. Then I would like to check whether Mr. Singhal, are you with us now?
Yes. Hello, everyone. I'm here.
Oh, okay. 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 Let me first introduce Mr. Vaibhav Singhal. First, Mr. Vaibhav Singhal is the Vice President, Design Elematic India. He managed the building design team who provide structural engineering and complete BIM solution to customers globally. He is a civil engineering graduate from Indian Institute of Technology, Kanpur in India. He is having a more than 12 years of rich experience in structural engineering for buildings and in building information modeling, BIM. He has designed various types of precast or cast in situ reinforced concrete structures, low to high rise, up to 50-story, villa, residential, commercial, industrial, and office buildings. He has spearheaded the large-scale projects covering various design stages, from concept design to construction stages. Mr. Vaibhav Singhal, I think time is yours. We have 45 minutes presentation and then continue with 15 minutes Q&A. And for participants, please write down your questions in the chat, whether in Bahasa or English. I will help you to translate it to Mr. Singhal.
All right.
Okay.
Thank you. Please let me know if my screen is visible.
Yes, visible and clear.
All right. Thank you.
Yeah.
Yeah. So, hello, everyone. So in this presentation, as the subject suggests, I'm going to mainly talk about the uses of precast structure elements in seismic region from the industrial perspective. Now, I come from India, and India is a seismic country. And all parts of India, we see there's a moderate to high seismic areas. And in India, so far, already more than 35 precast plants are already set up, and variety of buildings are being constructed using those kind of precast plants, right from villa to a high-rise 30-40 story buildings. Those are being already constructed. So before I start with the topic itself, let me just introduce you to our company, what we do. So Elematic is a precast concrete technology company. We set up precast plants globally. We are a technology company and market leader in precast concrete for residential and non-residential buildings. So, I mean, if we divide the buildings, there are only two types, residential and non-residential. In non-residential, we are talking about more of a commercial buildings or industrial buildings or hospitals. So those kind of buildings. Elematic facts in brief. So we were founded in 1959 in Finland. It's a Finland-based company. We have got a plant manufacturing unit based out of Finland, India, and China. We have got a presence in more than 50 countries. And if you can see all the dots across the world, that's where we have got our presence. And we have already supplied more than 4,000 precast plants worldwide. And that's how you can see our presence in almost in 100 countries. We have supplied the precast plant. Now, globally, our hollow core slab technology has got a market share of 60%. So that shows the kind of adoption and the market leader that defines us. So what we offer as Elematic, right from the concept stage of the project, we provide the building design solutions. Then we design the precast plant as per the building requirement for construction, for whether the type of building is residential or non-residential. According to the project requirement, we design the plant, that what kind of machinery is required. Then we supply the precast machinery to the customer. We set up the precast plant for them. And further, we also help the customer with respect to concrete mix design, also how to produce precast elements, how to install precast elements, and how to manage the overall logistics of the precast elements and the construction. So we are actually able to provide a total hand-holding support to our customers who are new to the business or who wants to learn how to do precast construction. So it's not just supplying the precast construction technology, but we are also helping the customer to materialize the dream of utilizing precast and taking the best advantage of the same. So you can see that all these things we are able to do with a very strong team of structure engineers and BIM professionals. Now, why BIM is also very important with respect to precast, because as you can understand, it's an off-site construction. You're constructing all the elements off-site, then you're bringing the elements at site and jointing them together. If we really put the entire process in nutshell, this is how it is. So it is important to design all these elements using BIM software so that all the elements which are produced in factory, they fit very well at site. So we have a strong team of structure engineers and BIM professionals. All our projects we are delivering through BIM software. Then we provide a complete project support right from supplier of the machinery and providing any kind of a problem coming in terms of operating the precast plants. So our service team is available. Then we also have a team of service engineers in India, which are also helping the people in India as well as global customers, where we are able to install precast plants. Then further, we also support customers by supplying any kind of a spare parts, and help desk is also available. And we are also able, as I mentioned, we have a manufacturing plant in India for mold manufacturing. So Indonesia is also being a neighbor to us. We are also able to supply a plant very fast. Now coming to the design team strength and the snapshot. So it is very important to have a very rich knowledge in terms of structure engineering first, because I just put precast construction technology is just an alternative way of doing construction. I mean, if you really look at it, we have a conventional way of doing construction, that is RCC. Then we do steel structure. Then we are using precast. So it is a third way of doing construction. Then there's also a possibility of using a composite structure, where it can be a combination of cast in situ, precast, or steel structure. So what is really important here, to design any building, one should have a very thorough knowledge about structure engineering. Then, so we have a team of very strong structure engineers who are graduates from Premium College in India. And together we bring a 40+ years of industry experience in terms of structure engineering for all type of buildings, whether it is a cast in situ, precast, or steel structure, or combination of everything. We refer not only the Indian codes, but we extensively refer American code as well as New Zealand code, which are quite advanced in terms of design of precast buildings. And we also refer European code. Now, when it comes to design of precast buildings for seismic areas, then definitely American code and New Zealand code, they have done a lot of research and they have provided a lot of literature to design those kind of buildings. Then for analysis and design, we are using various type of softwares, some CSI softwares. And then on the BIM side, we are using, again, various BIM software. So our team strength is, first is definitely the precast design, with the high-rise building design. Then pre-stress concrete design, that also requires a lot of skill set, because the pre-stress, we are stressing these tendons with high amount of forces. The production as well as the overall building performance has to be designed correctly. Then other than the engineering part of it, the detailing part, and further, the design is only and the quantity estimation through BIM. So further added services also we are able to support to the customer, to the client, or to the owners of the project, so that they are able to complete the project within time, cost, and quality. So this was all brief about Elematic structure engineering and design team strength. Now I'll talk about the precast structure scheme that we are adopting in India, and also for some of the projects that we have done outside India. So coming to the residential building. So one important aspect about precast is that the precast solution is very much important with respect to the type of building it is. Because at the end of the day, why somebody wants to use precast is for the speed of construction. Now, speed of construction is not only limited to the civil construction, but we also have to see the finishing of the building. So we have to adopt a method which can minimize the finishing work, and that's how the overall construction is done faster. So as in residential building, you see that there are a lot of infill walls, and that's how it makes sense to go with the load-bearing wall frame structure, where my walls will act as a gravity wall, as well as a lateral load resisting system as a shear wall. So that's why we call it for residential building. It would be a load-bearing wall frame structure, where you'll see that all these walls are basically load-bearing walls, which are acting as a gravity load as well as for the lateral resistance in both the directions. Then we have a slab which is spanning one way, which will just rest on this wall here and the wall here. And all my internal walls can be non-load bearing wall, still precast, but they would be like non-load bearing wall. So with this, I'm able to bring more efficiency in terms of the material consumption. I'll tell you how. So first is that with the usage of pre-stressed hollow core slab, I'm able to reduce the concrete and the steel consumption because it's a pre-stressed element. And at the end of the day, I'm providing more flexibility to the end user, because these kind of non-load bearing walls can easily be knocked out if required later on, or some modification to be done by the end customer. They are free to do it. So as a structural system, as far as the structural system for seismic areas is concerned, it is a load bearing wall frame structure. But in terms of taking the full advantage of the precast solution, we can do the facade also precast with any kind of a brick finish or color concrete. So like here you can have a brick finish or color concrete, or it can be just simple exposed concrete. So you're able to finish your building also very faster with minimum finishing work required. Then all your staircase is also precast. And depending on the design, architectural design of the residential building, there might be some few column or beams are required to support balcony, those kind of structure. So primarily, if you look at it in terms of structure elements for residential building, one is the wall and other is the hollow core slab. Now, one more important aspect while choosing the precast technology is also to see that what is the faster way of doing production of elements as well. And that's where hollow core becomes a winner, because you're able to produce, I would say, even 4 million square feet or 5 million square feet yearly or 6 million square feet yearly hollow core slab very fast with minimal manpower required, as less as probably 10 people doing the entire slab production. So those kind of industrialization of slab manufacturing is possible with product like hollow core slab. So that's how it makes sense to use this kind of product, especially in residential buildings. So this is a solution for residential building. Now I'll come to the commercial building structural framing. Now I've taken an example of a project where you can see standard. We always have a core area, which will be combination of lift and the staircase well. And then we have an office area where it's more of a, normally it can vary from 8 meter to 11 meter kind of a span in both the directions. So again, as we see in all the commercial building, or let's say non-residential building, it's a very open kind of a structure requirement architecturally. So in this kind of a structure, we cannot go with the load-bearing wall frame structure because I am not allowed to do that. So what we propose normally, that will have a combination of wall as well as column beam structure. Now, so all my office areas or where the space to be utilized, all this would be precast column and beam. And then I'll only utilize the core as a shear wall system. So in terms of precast elements, I would need column, I would still need hollow core slab. Then I'll go with beam. Beam can be pre-stress or non-pre-stress. Again, depending upon what kind of equipment are available, what kind of precast elements are available in the vicinity, and what kind of span is there. So the span also, because pre-stressing, definitely there is a cost efficiency with respect to material saving. Then shear walls also can be cast in situ or precast. Again, this will depend on the number of walls available, what is the plan area of the building, what is the height of the building. So in case of shear walls, it can be 100% precast wall. It can be combination of cast in situ or precast, or it can be 100% cast in situ in some lower stories. And then as we move up, it can be precast again. Then we can definitely have staircase. And Aquatech partition wall is again a precast solution of non-load bearing walls. Now, so this is a typical structural framing. Now, the advantage you can see that you don't really need to put beams in both the directions that you end up doing while we do the conventional design. So what we are suggesting is that you'll have a column beam structure majorly to support the gravity load. We don't really need to make column beam as a moment connection. It can remain as a column beam only as a pin connection detail. And all this column beam structure is designed to take the gravity load. And all my 100% lateral load is to be registered by the core wall. That is normally at the center, or it can be spread throughout the floor plate as per the architectural design. So in terms of, again, structurally speaking, that how the flow of forces will happen. So they are, as we understand, there are two types of loadings that we have to take care of. One is the vertical load, and other is the lateral load. So vertical load can be transferred through column beam structure. Now columns can be a multi-story column as well if it's a low-rise building, and then we can have a beam. So again, all these schemes is to kept in mind to achieve the better speed of construction, because that is what the whole advantage of going with precast. So we want to simplify the connections as much as possible, as per the, obviously, if the architectural design allows that. Then in terms of lateral load resistance system, it is important to first of all have a very good diaphragm of this slab. And this floor diaphragm definitely has to be designed so as that all the forces from the floor flows to the core area in both the directions. So that way I'm able to stabilize the structure laterally in both the directions, in X and Y direction. And normally, in order to provide a very good rigid diaphragm, we go with the reinforced concrete topping that is over and above the precast slab. And that is also a requirement in some of the codes. It's a mandatory requirement. Like in India, it's a mandatory to have a minimum of 60 mm RCC topping, especially with respect to mid-rise and high-rise building. In high-rise, it even goes up to 75 mm RCC topping. But those kind of toppings we can also utilize for gravity load design by making the hollow core slab as a composite slab along with RCC topping. And at the same time, that will provide us a very good diaphragm that is able to flow the forces to the core. And all my column beam structure would be a very simple construction with respect to production of column elements and production of beam elements. So this is again one solution with respect to every type of non-residential buildings, where it can be a simple column beam structure and core can be shear wall, which will take care of all the lateral load. Now, other than the commercial building, now industrial building also, there is a good amount of utilization of precast possible. As we have seen in industrial buildings so far, the approach is that up to plinth level, we do cast in situ construction, and superstructure is done 100% pre-engineered building with steel. And that is also providing us a good amount of speed of construction. Now, what we are proposing is that with the uses of precast, not only you are able to save cost of the construction, but also you will minimize the cost of maintenance of the building with respect compared to the steel structure. So what is the solution we are proposing? That even right from the foundation, because industrial buildings are low-rise building, is 1 or 2 story building. And in those kind of industrial buildings where the loadings are low, because of the virtue of being a 1 story or 2 story, and let's say the soil capacity is also good, not very bad. In those kind of scenario, even the footing can be precast. Our footing along with pedestal can be one precast unit. Then we'll have a plinth beam. Those plinth beam will also be in precast. And then the superstructure columns can be one single column right from the plinth level till the roof, can be in precast. And then we also have a mezzanine floor. Now in mezzanine floor, normally we have seen that if we go with the steel structure, it will be a deck flooring. And because of heavy loading at a mezzanine floor, deck flooring become quite expensive with high consumption of structural steel. Now with the uses of pre-stressed hollow core slab, with the uses of pre-stressed precast beams, we can minimize the concrete and steel consumption, and we can make very cost-efficient mezzanine floor construction. And then further at the roof level, we have a choice. We can make precast, but normally at a roof, we have seen that the span goes 20 meter, 25 meter, it can go up to 60 meter. Now in those kind of scenario, if we unnecessarily put dead weight of the precast elements, it will not really be that much helpful. And also the transportation of that long precast elements also become problem unless you are doing the precast element production right next to the site. So in those kind of scenario, it will make sense to keep the roof as it is in structural steel, which would be lightweight. So in nutshell, if I look at it, only the roof part can be done with the structural steel, but rest of the elements in the structure, right from foundation till the roof, all the elements can be done in precast. And in some warehouse where you have got some kind of a EOT cranes running, which are heavy loading again on the columns, and there you will see even more cost efficiency with respect to these column design. So all these advantages are there if we start using precast elements in industrial buildings. And this is gradually catching up in India, where it is more of a hybrid solution, I will say, where it can be, I mean, it's a combination of, we can put it that even, let's say foundation, if it, let's say it's cast in situ. So we are also having some cast in situ elements, we are having precast elements, and we are also having a structural steel elements. So it's using the best of best technologies and coming up with a very cost efficient and more durable solution for the project. So we have seen that pretty much all type of building precast solutions, whether it's a residential, commercial, or industrial buildings. Now, in all these buildings, you must have realized the kind of precast elements are required are only 5 elements. Doesn't matter what type of building has to be done. We only need, one is the slab, then you need wall, you need column, you need beam, and staircase. With these 5 precast elements, you're able to pretty much do any type of building. And that is the advantage with precast technology. I'm not talking about just doing a precast construction using some formwork that we normally can be done for any project. It's like, you know, just doing same cast in situ work offsite. But using some technology like Elematic precast construction technology, you can actually have a very pretty much flexible plant which can cater to all type of projects, all type of architectural design, and without making any changes to the mold. And that is the kind of flexibility you get in your machinery, that you are not really restricting the architectural intent or architectural design, and yet providing the structural solution. So if you have a standard precast plant, you are actually able to cater all type of precast buildings and all type of different architecture. I would say at least 90% of the architectural requirement can be served through these kind of precast plants. Now, with respect to slab solution, other than the hollow core slab, there is also a possibility that if, let's say, it's a long car park, or we talk about this industrial building, if somebody wants to do even roof with precast, so double T slab is a solution which can go up to 25 meter, 30 meter span, or even beyond that, we can even go up to 40 meter span. Then there is a half slab solution. If somebody doesn't want to use hollow core slab in residential building, then half slab is another solution where it can be only plank part is precast and balance thing is done as cast in situ. So this is more of an emulative approach of cast in situ slab, where you're just removing the formwork you are putting the formwork as itself as a precast element, and you'll definitely have a props while doing the construction, and put the topping on top of it, and your slab becomes one composite site. Then we can also have a solid slab, which is again 100% precast. So there are various slab solutions, again as per the project type and architecture intent, those slab solution can be utilized. And that definitely also depend, the design also will depend on the span, loading, and the availability of those kind of precast elements in the vicinity. Now talking about the connections which are prevalent that we use. So this is a typical connection detail for residential projects where it's a slab and wall solution, where you can see that it's a load bearing wall frame structure where my slab is coming and directly resting on the wall itself. Now you'll have some certain amount of bearing. Those calculations are available in the code, as well as we have to check with respect to the bearing stresses. So in terms of this connection detail, if you look at it, there are few things that I would like to highlight. One is that we want to avoid any kind of a progressive collapse of this building. So this wall should be well connected with the slab. And that is also possible by providing one reinforcement going inside the topping. The other thing is that you want to connect the wall with the wall above. So in that case, this reinforcement from the wall below is going inside the wall above. And then you are simply doing the grouting of this joint. This is a dowel tube, which is basically this dowel reinforcement is going inside the dowel tube, and it is filled with the grout. And even the gap between the two elements, which is normally around 20 mm, is also filled with the grout. And if this being an exterior joint, then definitely from the waterproofing perspective, there has to be some application of sealant done from the outside. So it's a very simple connection detail which can be executed at site. And this is definitely a seismic connection detail. Obviously, the spacing of the bar, the diameter of bar, all those has to be calculated with respect to the height of the building, the type of the building. So it's a very simple connection detail which can be easily executed. And the only thing that has to be well inspected at site is the joint part, as we all understand, because all elements are done in the factory which are of very good quality, but special consideration and the attention to be given at site while doing these kind of connection at site. Then, so this is a wall to slab connection detail and also wall to wall horizontal connection detail. Now, wall to wall vertical connection detail is, let's say, if I want to make this wall as a monolithic shear wall from this end to this end, then I have to go with the stitch connection where there is a reinforcement projecting out from both the sides, and then I have to fill it with the concrete at site. So if I don't want to make this kind of wall to wall as a monolithic connection, then I can even go with the loop connection detail, just loop coming out from both the sides. Some wire loops we call them. And then this gap doesn't have to be this big, which is normally 500. This gap can be reduced to, again, back to 20 mm gap, like this 20 mm gap here from exterior side. And then from interior, we can have around 50 mm gap. So again, this is all related to how structural engineering is defining the flow of forces with respect to gravity load as well as with respect to lateral load. So structurally, if let's say I don't want to have this long shear wall, then I can have two independent shear walls which will act independently in the event of earthquake. But for gravity load, I'm providing some loop connection so that there are no cracks visible during the serviceability of the building. Further, some more connection details with respect to column and beam. Now, with respect to column and beam, again, it's a choice that whether it has to be a moment connection or a pin connection detail. Now, what you're seeing at the screen is a moment connection detail, where you're actually doing a concreting of this column beam connection, where the bottom reinforcement is also projected out, and then top reinforcement is also continuously going. And this bottom reinforcement projection also be some minimum development length has to be there so that it is well embedded inside this in-situ concrete. And after doing this, this will behave as a very good moment connection. And we have also seen in the last presentation that the performance of this connection is very good. And this will also behave as if it's a cast in situ connection detail. Now, similarly, in case of column to column, the connection detail is also similar to what we have in wall to wall connection as a horizontal connection detail, that you will have a dowel reinforcement projecting out from the below, and then there's a dowel tube, and then you lower the precast element and you do the alignment, and after that you fill it with the grout, and then your connection is done. Now, the other approach, if let's say these kind of dowel tubes somebody doesn't want to utilize, because especially when we talk about mid-rise and high-rise building, the diameter of bar will go up to 40 mm or 32 mm diameter bar is being utilized. In that case scenario, the development length also goes up, and these projections of the bar might reach in the range of 1.5 meter, right? So in order to minimize those kind of projection of dowel reinforcement, we can choose to go with couplers, which are grout-based coupler. So in place of using this kind of dowel tube, we will just simply have a coupler, and this coupler height again will depend on the type of diameter of the bar, but then your projection of the bar is limited. So it's only, let's say, probably in the range of 500 mm, not more than that, especially if I talk about 32 mm or lesser than that, probably 400 mm. And then you'll have a bar from the precast element that is already embedded. And then you only grout this coupler. So this definitely simplifies the way construction is done and the way precast elements are produced, because having a long projection of bar is also become problematic while we are transporting the precast elements from the factory to the site. Then even for connecting the bottom bars, also we can use couplers, which can just slide from one bar to another bar, and then this can be grouted. So with the uses of couplers, we are able to improve the precast construction efficiency, and this connection is also will behave as a monolithic moment connection. So this is one of the examples. Now, further talking about some connection details, this is a snapshot taken from an industrial building project. So just to talk about also on the pin connection details. So in case of pin connection, the difference is that my bottom reinforcement need not be going inside the column beam connection. So it will just, the beam will come and rest on the
Hello, Mr. Vaibhav. Mr.
I think
Singhal.
there is some
connection problem.
connection problem.
Yes.
Let's just wait for a while.
Yeah. Okay.
Okay. We just wait for a while because some connection problem, I think. Let's see. This is the challenge of webinars with many participants.
Sorry, I think my connection was lost, I believe.
Yes. Okay.
Yes.
Please.
Yes, Mr.
You can
Singhal,
join again.
please. Yes.
Okay. Sorry for that.
Yeah.
So was I on this same slide, because I'm not sure if I missed too much or.
Yes. It's
Yes. This slide. Yes.
Okay. All right. So yeah, so I was talking about this pin connection detail. So in place of pin, I mean, we can also have a pin connection detail where you can see the advantage is with respect to production of precast element. I don't really need to take out any rebar because that is also something that has to be done in the factory. So the production becomes more complex. But in case of pin connection detail, I am able to produce elements in a very efficient manner. And also installation is very easy to do. So it all depends. Structurally, if I'm okay to go with the pin connection detail, then definitely it will have a construction advantage. So this snapshot is basically from this industrial building project, where right from the foundation, you can start doing the pedestal and then the main column. In the industrial building, you also have those kind of storage, those kind of dock area where your truck will come and then do the loading and unloading. Now, even that dock area we are seeing, because of heavy usage of that particular area, there is a lot of, tear and a lot of maintenance is required because of the heavy uses. So it's better to do with the reinforced precast elements in the dock area with just solid wall and solid slab. And this will ensure that good low maintenance of the building. So it's more of exposed concrete. So this was all I wanted to talk in terms of the precast structural scheme for residential and non-residential projects. Now I'll just give you some examples of precast projects in India. So it's a large police housing colony. It's a group housing project. It's based out of 6 peak zone 3. So India is divided in 4 seismic zones, where seismic zone 2 is being the moderate or mild earthquake zone. Then zone 3 is moderate, and then 4 and 5 is more severe. So in seismic zone 3, where there is also a mandatory requirement for ductile detailing, from seismic zone 3 and more, we have to do a ductile detailing. So in this project, it's a 4 million square feet large residential apartment project, where there are 60 towers under construction, and it's a G+14 building. So you can say it's a 15-story building. And here the precast element we used is the similar that I was talking about. It's wall, slab, and staircase flight. In case of slab, it was a pre-stressed solid slab used because that was the choice from the client, that he didn't want to use the hollow core slab. But as an element, these were the elements used. So now you can see the project as such, some photos from the site. And you can also very well gauge that, how less people are required at site. Here you can see the installation of wall is happening. And to install these walls, you can only count people, like 4 or 5 people are just standing there to install this wall. And they will just do the jointing of it. So you are actually able to erect on an average 1 element per half an hour. So you are able to, they are able to achieve 4 to 5 day cycle per floor. So that is the speed of construction you are able to achieve. And the other advantage you are able to get, especially with pre-stressed slabs, like you can see all our pre-stressed slab, one-way spanning, is that right after installing the slab, you can start doing any kind of architectural finishing work required in the building. So you don't really need to wait for next 15 days before, that we do normally in conventional construction, that unless that slab achieve that strength, then only you remove the formwork, and then only you're able to do the finishing work. And that is not the case with precast construction. So to put it this way, let's say you take 12 months time to complete, just hypothetically I'm talking, let's say you take 12 months time to complete the civil construction of the building, then you'll take only 1 month extra to do the entire finishing of the building, because all your finishing work can go parallel to the civil construction. So that is also an added advantage with precast technology. Some more photos. And here also you can see they were not using couplers. So you can see the large dowel reinforcement projecting out from the wall below, and that are actually going inside the wall above. And that's how the precast wall construction is happening. So, what we understand, if the building is designed good and it is detailed properly, then production becomes very easy. The production of elements, if production of elements is done good, then installation is just a Lego game. It's a child's game. You just have to fit the elements with each other and do the jointing properly, and things will go very fast. So it's, I mean, compared to conventional construction, it's a lot easier way of doing construction. Now there's another example of a precast building. It's a 24-story above ground, and then there are a basement, 3 basements below ground. This project is already constructed and finished. So the elements that were used were hollow core slab, pre-stressed beam, and the precast column, precast wall, and staircase slide. In this project, this column to column grade was in the range of 11 to 13 meters, and that's how they were able to provide longer spans, and that's how you increase your car parking efficiency in the basements, because that is also a requirement, especially in commercial building. So you can see a photo of this building where all these columns are 1-story precast column. Then we have a pre-stressed beam, and then obviously the hollow core slab is spanning in the other direction. And all these walls, which are acting as a shear wall as well, these are all precast shear walls. So structural system here is a combination of moment frame at the perimeter, and then the precast shear walls as far as the lateral load resistance system is concerned. And for gravity, it's all column beam structure. So this photo you can see is building is right now is already finished, but this is already at a last stage and last floor of the building. And you can also see multiple cranes just functioning here and doing the construction of the project. So more closer view of the building. Here you can actually understand the structural scheme much better, where you can see the hollow core slab is spanning from beam to wall, because this is a core area. And now these columns, again, they can be a multi-story column as well. But since this being a very high-rise building, we also have to see the weight of the element as a consideration, because the weight of the element will also define the capacity of the crane. So if there is a high capacity crane available, then definitely we can even go further with the double story column or bigger size of the column. So here you can see how the hollow core slab is being erected here. And then afterwards, the topping is done. Now, obviously, how the construction scheme is planned, like at some floors, it can go up to 2 or 3 floors. At some places, you can be at lower floors. So those kind of staggering of the construction is also possible. And then obviously, after the slab is installed, there's a uniform topping is done to have a rigid diaphragm. As you can see here in this area, there is a reinforcement already placed, and they are connecting bars which are projecting from the beam itself, which will be bent inside the topping, and then the topping is done. So now this is a project that I also wanted to talk about. This is an ongoing project that we are doing right now. It's a 40 million square feet development that is happening again in south part of India, where it's a 12 towers. And the important part is it's a 43-story building. So 34-story above ground, and then we have a 7 basement, and there's LG plus UG. So 7 plus 2 plus 34 is what makes it a 43-story building. One tower is a 2.5 million square feet development. So this is already the foundation work is happening at site. The design is already progressed to that level. And now you can see this is going to be a tallest precast construction, 43-story building ever done, I would say, globally. And in this particular project, we are able to provide a complete hand-holding support to the customer, right from the structure engineering from the project, then also setting up the precast plant, and also designing the plant. And we are also helping the customer with production and installation. So we're providing a total precast solution to the customer. And their target to build this project is with the speed of 5 million square feet every year. So especially in a developing country like India, and I believe in Indonesia as well, this is the requirement and the demand that we have to go with the faster construction, which is quality wise very good. At the same time, you're able to achieve the speed of construction. So this is under construction, and this is a landmark precast project coming up in India right now. So this brings me to the end of presentation. I would like to just play a small video, if the time permits.
Yes.
It's about the same. Yeah, it's about the same office building project from the customer that I would like to show. And I would also like to, mention that hollow core slab is a very wonderful product, as you have seen. And this is such a versatile product that is being utilized in any type of building, whether it is a residential building or commercial building. And I believe in Indonesia also, Elematic has already supplied a precast plant to Vietnam. They have got several lines of hollow core slab. And this is such a versatile product that can be used for every kind of precast projects in Indonesia. So let me just now play a video. Let me just know when it's visible.
Not yet running.
Just a second.
Yes.
So
But
it is
sound. No sound.
Yeah, I think I'm sure you'll be able to hear the sound, but I'll explain this also, and you'll also get a subtitle here.
Okay.
So this is a large precast factory that we have set up in the south part of India. As you can see, there are 6 beds of hollow core slab, and then they are also having a land area of 24 acres, where the factory area itself is in 8 acres. It was established in 2019, and this is the same project that I was talking about, where you can see this construction is moving forward. So it's a commercial building for the office spaces. So yeah, so they are doing 10 million square feet building. So for all their commercial as well as mall kind of project, they are using this technology, and also in the residential buildings, especially for car park area. And I would say that why it's speeding up this utilization of technologies in India is also because of the scarcity of manpower, and that is also delaying a lot of castings into projects. So now this is a hollow core slab plant, and you can actually see that how the construction is done with using very less manpower. This is a beam production line. So they have got a plant far from the site. You can see that all these elements are manufactured in a very stable factory. I mean, far from the site, and they are able to cater to all their projects in the vicinity of 150 to 200 kilometers. Okay. So this is how they're doing the pre-stressing. So with respect to precast plant, I would also like to mention that this kind of concrete transportation, because it's more of a complete automation of the factory, that right the batch mixing plant, you are transporting the concrete to the mold, Then mold is also having technology in terms of compaction, in terms of casting, and that's how you're able to minimize even the manpower in the production facility. And then you're so we are also minimizing the uses of water and then recycling of water. So all these advantages are there with respect to going with the construction technology, and we're able to come up with very good the concrete transportation happening from the mixing plant to the mold and machine.
Excuse me, Mr. Singhal, can we proceed to the question and answer now? Because we have several questions already waiting for us.
All right, sure.
All right, sure, okay. And then we will go to the first question from Mr. Gambiro. First question is, how are the details of the connection between the HCS and the moment-bearing frame beams so that the HCS can function as a diaphragm?
Right.
Yeah.
So from hollow core slab to the beam, definitely we have to open few cores so that we put a reinforcement coming from the beam inside the hollow core as well. That I think in the last presentation also, that was from the Professor Hari, it was included, and that is also available in the design guidebook. That yes, we have to open a few cores in the hollow core. We have to place some reinforcement, and then core has to be filled with the concrete. And that's how we ensure there is the connectivity of the hollow core slab with the beam. And as well as, but as far as the diaphragm is concerned, the diaphragm is being designed through RCC topping alone. So we are not utilizing hollow core slab as a part of diaphragm. We are only utilizing the RCC topping as a diaphragm.
Okay, I think it's very clear. Yeah. For the second question is from Mr. Christian Gilbert from PT Tata Mulia Nusantara Indah. First one is there any factory project that using precast foundation, that using precast concrete component such as mass concrete above the ground for turbine generator foundation? Because besides seismic load that occur periodically, there's also dynamic load or vibration load that occur inside the structures.
I'm not sure if I got the question correct, but we are talking about the foundation of industrial
precast foundation for the turbine structure, because we have the vibration load. Yeah.
Okay. So see, first of all, with respect to foundation, we have to understand the size of element, because if the size of element is too big, then definitely it will not make sense to go with precast. So I'll put it this way: if your foundation size is, let's say, less than 4 meter by 4 meter, because you have to transport those elements also to the site. So if it is less than that, then you can transport it. But as far as the performance is concerned, so see, at the end of the day, the precast foundation is also a reinforced concrete element. So it has to be designed keeping the same cast in situ design principles. And performance-wise, the material is same. It's a reinforced concrete. So performance-wise, there is no issue. I mean, it will perform equally.
Okay, so the performance is not an issue, but the size is matters, right?
Yes. Because you have to see the weight of the element, also the overall geometry of the element.
Yes.
And if you're not able to transport and lift, then it will not make sense to do precast, right?
Yes. Okay. I think it's very clear. Okay. The second one is, does the length of splicing overlap rebar or the anchorage of precast concrete have the same length with conventional concrete? The overlaps. Okay. Yeah. And what is the difference with using chemical rebar for seismic constructions?
See, as I suggested, we can use couplers. Now we can go with the grout-based coupler, and with the grout-based coupler, you are able to make these rebar to rebar connection very strong connection. So in case of seismicity, in case of earthquake, my rebar will not yield within the coupler. It will yield outside the coupler. So then it's just the rebar yielding, right? So the coupler we can use if we want to minimize the length of the rebar.
Okay. Okay, we move to the third questions from, now is from Professor Benjamin. In the police housing that you presented, how do you measure the continuity of the shear wall? The police housing colony, as I remember, yeah.
Yes.
How to measure the continuity of the shear wall?
Yeah. So see, in India, I understand that at times one is that emulative design approach where all the reinforcement is continued right from the foundation till the top. But the other scenario is that we can do the lapping of reinforcement. So what we are providing is the dowel reinforcement, and that is lapped with the precast element wall reinforcement. Now this is more of a jointed precast elements, but the performance of these kind of connections has been tested in New Zealand, also in America, and that's how they have given those kind of precast connection details, that these connection details will also perform equally good as if it's a cast in situ construction. So as far as the shear walls in this housing project is concerned, it is done through dowel connections. As you was able to see that there was some dowel reinforcement projecting out, going inside the dowel tube, and then it's filled with the grout. So that's how the connections are done.
Okay, using the dowel, right? Yeah.
Yes.
Okay. And then we proceed to the next questions from Mr. Amin Hudaya from Petra Studies. Please kindly show us in more detail all the joint systems for all precast elements used in those high-rise projects. If you have the presentation slide, would you like to share?
If you saw those connections that I talked about with respect to wall and with respect to column to beam, I mean, these are the only connection detail that we have used, because these, if you see in this high-rise building, it's a column beam structure, then there is a hollow core slab connecting with the beam, and then there is a column to beam connection. So all these connections I have already taken care in the presentation. It's only about how further detailing to be done with respect to the diaphragm reinforcement. But definitely that I don't have readily available right now to show it. But principle remains the same in terms of how this column and beam connection to be done. Like I saw that, I mean, I show that column to beam as a moment connection detail. Do you want that me to pull out that slide again?
Okay. Sure. If you like to share your slide, please.
Yeah, I'll just do that.
Yeah.
Just let me know when it's visible. It's visible now, I believe, right?
Yes, it's visible now.
Yeah. So if I talk about this column to beam connection, so you can see this is the column to beam connection detail. When we are talking about, it's a moment connection. So at the perimeter, we have used this kind of a connection detail where bottom reinforcement is also jointed with each other and top reinforcement is continuous. And we have used coupler for the column to column connection. While it comes to hollow core slab, there could be a scenario that hollow core slab is coming and resting on the wall. Now, in the lower story, we might have, we had actually 2 layers of dowel connection instead of just single dowel, because the wall thickness in the lower stories is somewhere in the range of 350 to 300 mm. So when the thickness of wall is more, in place of single dowel, it will become a 2 dowel of reinforcement. Then when we had to connect this wall to wall with each other, it's still this kind of a stitch connection detail. Let me just remove this markup here. Right. So this kind of a stitch connection detail. And then if it is about just going with the pin connection detail, let me just remove the markup.
Yes, I think it's okay, Professor Mr. Singhal. Another following questions is, are all systems already past the cyclic load test?
Yeah, so in our university also, the typical column to beam connection seismic test has been done. And there also the reports were found satisfactory. And that's how it is well adopted. And our code also allow our code does not really emphasize on the emulative design approach. We can go with the jointed precast elements or any other mechanical joints as well, as far as it is performance is satisfactory with respect to the kind of load to be applied on the building. So, yeah.
Okay. We move to the further questions from Mr. Joe from DSP. Can HCS be considered as composite action with topping slab for diaphragm? Do we need to provide detailed connection between HCS and topping slab?
See, you can only consider HCS along the length of the hollow core slab as a composite diaphragm, because only along the length you can consider this as a composite slab. But on the across the section where every hollow core is a 1.2 meter width, and then between the two hollow core there is a shear connection. So across the width you will not be able to achieve composite action. So there it would only be a topping acting as a diaphragm.
Okay. We still have around 5 minutes. Any questions from participant can ask Mr. Singhal lively. Oh yes, there's one going to the chat from Mr. Cheong, perhaps. Is that what is the design criteria for determining dowel bars between wall-wall connection? Should the dowel bars designed to resist horizontal shear of the wall or need to have equivalent area of wall vertical rebars?
So definitely, I mean, when we are designing the walls, we are considering this as a continuous shear wall right from foundation till the top. So whatever forces that we are anticipating in terms of axial load, in terms of bending moment along the length of the wall, and in terms of shear force. So for these three forces, we have to design at that particular joint. So we get from the analysis software, we get the forces, and then for those forces, we have to design those dowel reinforcement.
Okay, so we need to consider it, right? Yes.
Yes.
Another question is coming from Mr. Harj, I think. Yes. What are the main obstacles in the development of precast buildings in India, and what are the strategy to develop the precast building market in India?
See, earlier definitely there was some challenges with respect to acceptance of precast solution with the structure engineers, also with the government, because of the lack of awareness. And those were the times, I would say, 10 years back. And in last 10 years, I mean, we have been present in India for last, I would say, 15 years now. And so initial 5 years were tough for us, where we had to talk to structure engineers, where we had to talk to all the professors and also the government bodies. And then with all the research papers and the testing done, and it was widely accepted. And now we are at a situation that it has already been accepted kind of structure engineers, and also in the government tenders, this has been also put as a preferred technology method. So even there are some tender documents where specifically define they have to use precast technology for doing particular project, because that's how government is also gaining more confidence with respect to quality and speed. Because see, one more thing we have to understand is that precast provides certainty in the construction. Like, you know for sure that this project would be completed within 2 years time or 1 year time, because all my construction activities are well defined. While in cast in situ, there is a lot of uncertainty. So that is how, you know, acceptance is very much there now, and it's growing very fast. I believe that answered my question, or there was something else?
Yes, I think it's okay. I think we also face the same issues here in Indonesia, that we need to make others confidence with our design and technology, right? Yeah.
Right.
Okay, the next question is from Mr. Pamuda from Petra Christian University. During earthquake, do the code always design the connection to be stronger than the elements, or by design, the connections may also yield and should have ductility?
See, so connection can also yield. That is not an issue. It should have a sufficient ductility, because all our connection details are also having sufficient ductility.
Mm.
So ductility is not overruled at all. So, but what I am suggesting is that when we go with the coupler connection, which is just part of the connection, so you will not have a yielding within the coupler, but just next to the coupler. So it is within the zone of the connection itself.
Okay.
Yeah.
I think this is the last questions because the time is running out now. It's also from Mr. Anin. Have you performed full-scale shaking tests on building using those precast connection systems?
See, we are the people from industry, so we just follow the research work done by the professors.
Oh, okay.
Also done by other universities in US and in New Zealand. So I believe they have already done, and that's how we are following the same literature. I mean, this is nothing new that we are using, is the same connections which are widely accepted. It's only the analysis and the design part we take care, and we provide the connections accordingly.
Okay, I see. Yes, we just adapted what have been done in the University of Research Institute, right? Yeah.
Yes.
Okay, Dr. Anthony and Miss Pamela, I think times is over. I will return back the session for you. I would like to thanks again Dr. Hari Nugraha Nurjaman and Mr. Vaibhav Singhal for your excellent presentation. It's very insight for us. Yeah, give very insights for us. Thank you. Please give a virtual applause for them. Yes, Miss Pamela, please.
All right, thank you, Dr. Aswin, for moderating our first session, and also thank you for all the speakers. Once again, I want to remind that the link for the certificate and feedback questionnaire will be shown at the end of this webinar. So please fill the form for your certificate. All right, ladies and gentlemen, before we come to the second session, we are now in a break for 15 minutes. The next session will begin at 13:45 Indonesian local time.